Welcome, everyone. This is the first Roku Engineering Symposium. I'm super proud that we can have this in Aarhus today. And we have a very exciting program for you today as well. We have two great speakers. We have our own Aaron Graham, principal engineer at Roku, talking about printf or type-secured printf today. And we have also our star of today, Bjarne Strustrup, who's going to talk about C++ in constrained environment. So we're very excited about this. And also, if some of you are very excited and want a autograph on your arm, a book, I don't know, on the leg, I don't know what you preferred. Be honest, said it's okay that you can get that. Yeah, so welcome. And we're super excited. And the reason why it's interesting for us, or why Roku spent so much time thinking about C++ or working with C++, is that efficient C++ code means a lot to us. If we can save memory, if we can save CPU power, means we can extend the life of our products, continue to add exciting features for our customers as well. So we try to utilize the width and the opportunities that there are in the language. And so, yeah, very excited about it. So I think with that, I'd like to invite Aaron to the stage for the first presentation. All right.
It's on. It's not on. Hello? All right. Yeah, like Brian said, I'm a principal engineer at Roku. I've been at the company for, well, I'm in my 15th year, actually. So it's been a while that I've been doing embedded software, and I was doing it before Roku as well. And the thing I'm going to talk about today is a type-safe printf. And I know a lot of people are probably rolling their eyes because everyone's got their own formatting library. That's not what I'm going to talk about. I'm going to talk about how to actually make printf type safe, the existing printf in the C library, using features of C++. So with that, it's called full circle because we're sort of returning to our roots. Okay, what is printf? It's a print formatter. Yay. But also, I think it's important to realize that it's a specific instance of, or it comprises a domain-specific language. It's a very simple language, but that's what it is. And so what you have is an interpreter that runs some code and that has some inputs. And the way that looks like, what that looks like with printf is something like this, where the function itself is this interpreter. And then the input string is sort of the code that you give it. And then you've also got your inputs. And then it produces some output, which in the case of printf is some formatted text. So all very simple, very old tech. So there's some problems with printf, and a lot of you probably have dealt with them before. So first of all, let me ask, how many of you like printf, like to use it in your code? Come on, be honest. So, okay, gives me an idea of how many people actually care about this. But maybe you'll like it when I'm done, so that's sort of the point here. So there's problems with printf. The first one is that the inputs are not guaranteed to match the format string. And that leads to things like this, where you can actually write this in code. It will compile and run. And if you're lucky, you'll get something like that. If you're unlucky, lots of things could happen. It could crash. It could print like an encryption key, depending on what parts of memory you're accessing. So what printf is doing is it's just taking items off the stack and interpreting them the way that the format string is telling it to. Now, there's a partial solution to this. the compiler extensions, and every good compiler has these. In the case of GCC, it's this format attribute that does the syntax checking of the format string for you, and you can apply this attribute to your own functions, and it will do the job of actually checking the types and making sure they correspond to what's in the format string. That's not good enough. The other problem with printf is that the format strings are not portable. At Roku, we do software for lots of different platforms. We have MIPS, we have ARM, we have x86 that we run our software on. We also have 32-bit platforms. We have 64-bit platforms. And so the format strings they're just not portable. And here's another example of something going wrong here. So in this case, we're putting the address of the name variable into the upper 32 bits of that int64. And then we're calling printf on it to print the int64. And in the case of a x86-64 with GCC, LX is the correct way to print that. uint64 is a long, unsigned long. And so if you compile this for x86-64, it works. It sort of gives you what you expect. Now, if you add the M32 flag for 32-bit compatibility, you get this instead. So, that wasn't supposed to happen. Now, in this case, okay, big deal, this is a contrived example, but the problem is that security exploits are always contrived examples. So if the variable that you're printing is something that comes from user input or from a config file, then they have a lot of things that they can do to access various parts of your code. And that's a big problem. So there's this thing, there's a class of security exploits called format string attacks, and that's exactly what this is. They're contrived attempts to attack you by using the format string and the corresponding variables that you're passing into it. There's different kinds of format string attacks. One of them is if you can generate the format string at runtime. Maybe the worst I've ever seen was somebody had a format string in a config file, and the user was allowed to change that. Okay, not a good idea. Don't do that. And so at runtime, it would take that format string and do a printf on it, and then just use whatever it expected certain variables to be the inputs, but if the format string is different, then it could do anything with those. So yeah, it's one of the things we really care about at Roku is being secure. All right, so how do we fix that problem? Well, C provides this library, int types, and what it is, it's a porting kit for format strings of standard types that are often used in C code. And there's a lot of them. And the way you use them is that you insert them into your format strings and sort of match them up with the variables that you're trying to print. Okay, well, that's good. But it's, first of all, if you've ever worked for a company or worked on a project where you're mandated to do this sort of thing, it's really hard to get people to write code this way. They might not even know that a certain type def is associated with a macro. And so they might just, it compiles, there's no warnings on this platform, and then check it in. It works. But even if you could get everyone to do this, it's still insufficient. And that's because in C++ there's types all over the place. There's a lot of types. It's just common practice to create a new type, and it should be, you shouldn't have to care about what type you're dealing with. It just should be sufficient for the purposes that you're using it for. And we can do a case study here of the minutes type in the kernel library. So if you're doing a printf of a minutes type, what goes there? What goes in that question marks? Anybody know? Okay, good. The standard says signed integer of at least 29 bits. So, well, that doesn't tell you either. All right, so why do we even want printf? We've got IO streams. We've got, as of C++20, there's the new format library, which isn't available yet in GCC or Clang, as far as I know. But you can still use it because there's a format library which has been around a long time, which has implemented it. And I actually looked into switching us to the format library back in, I think it was 2016, a long time ago, because we do all of our logging using printf. And we wanted it to be safer and better. One of the problems with that is the code size. We're very conscientious about code size at Roku. And if we're making a change to our code base that affects almost all the code and exists at many call points throughout the code, so there's lots of logging in various places, we don't want to make a change that's going to increase our code size substantially. So let's look at this. Let's say most of our code is actually compiled this way with thumb instructions, at least on ARM, and optimized for size. So IO streams gives you 28 instructions at this call point. Okay. And then format gives you 24 instructions. Anyone want to guess how many printf gives you? It's 5. So that's important to us. But that's not the only reason. We have some momentum there. Like I said, all of our logging is in printf. It has been since it was the logging system was created back in 2008. We can't make large sweeping changes to it. At least not without a lot of risk and a lot of work. So one solution is to stay with printf, and that's what we've done just because of the momentum all these years. So we want to keep it, but what we need from it is this list here. We need it to be correct. We need the security that type-safe system provides. We need it to be portable, and a bullet point I'll go over a little bit later. We would also like it to be a little bit more flexible. So for a couple of years, the solution that sort of bubbled around in my head was, what if I patch the compiler or change printf so that we can just have a %? Format specifier? I thought about it a lot. It would be similar to the way OStream overloads work. And actually, libc provides a couple of hooks for you to register your own format specifiers, which was interesting thing to discover. Unfortunately, it's not good enough because it doesn't tell you the types of the arguments that it's expecting. It's expecting you to know based on the value in the format string. And if it's just a question mark, you don't actually know. And even if we were to successfully implement it this way, it wouldn't be portable, right? Because if we're using a different libc, our code just wouldn't work. So C++20 came about, and I had my solution. I knew exactly what to do with this. One of the nice things about C++20 is it adds a couple more non-type template parameters that you're allowed to use. That's what CNTTP means. It means class non-type template parameter. And that's this last bullet point here. So you can actually define your own class and then use instances, not types, instances of that class as template parameter. And here's an example. This, you can instantiate this type, use it as a template parameter, actually transparently. So you can just put a string inside of a template parameter and use it that way. And that looks sort of like this, where you've got the first parameter there. First template parameter is the format literal. And then you use it like that. All right, well, why did I think that would be the solution? Well, it's because there's a lot of things you can do with that string at compile time. First thing you can do is compile time error checking. So you can have enforced error checking without using the format attribute. So then it's portable, it works for any compiler. And it might look something like this. So your printf function has the check types, and that just checks to see if the types themselves are mismatched with the letters in the format string. This is not a complete solution. I threw this together as an example. It's probably full of bugs, so don't use that. But it's an example of what you could do. And actually, libformat, formatlib, the library that I discussed earlier, has this. They will check the format string validity in exactly this way. And note the const eval on the check types. That guarantees that it must run at compile time. And that's exactly what you want. And if something goes wrong, it does that throw, and then it fails to compile. The second reason we want to use these strings as template parameters is the ability to not just check the string, but to rewrite it entirely at compile time. So one of the nice things about being able to do this is you don't need to care about those length modifiers anymore. You don't need to care about, if it's a long or a long or whatever type of modifier it might have. You just care that it's an unsigned integer. And it will see that it is, and it will rewrite the format string in this way. And it also gives us our magic print whatever format specifier. So the compiler knows what the type of X is, and it can associate that with the format specifier and just generate the correct one. But you can go further than that. You can actually incorporate support for non-fundamental types. So one of the difficulties with using string view is that somebody always wants to print one. And if you're using IO streams or some other library, it usually works just fine. But if you're using printf, it's common that someone will just call it sv.data in this case. And that's not guaranteed to be null terminated, so it might work, it might not, it might crash. So you have to print it in this way. And so this ability to rewrite the format string gives you this as well. And this is the flexibility that I had been talking about earlier. So that's what we have here. We have a compile time front end to standard I/O. It's not a replacement for printf. It's just something that happens to check the format string and then forward it to standard I/O. The internal details, I'm not going to show you a whole bunch of code here. some of it's kind of tedious. I mean, anytime you're writing a little parser, it kind of is. But this is the way that you would adapt any function, in this case it's printf, to have this capability. There's a few ingredients here. There's the build format, which takes the format literal that you've given to it as a template parameter, and it returns another format literal, which is the type, which is the string that actually gets sent to the printf function. And that's, as you can see there, const eval. So it's guaranteed to run at compile time. And it does this with a transformer class. And the transformer class, its job is to parse the string and then convert it to a valid format string. And I would like to point out that this utility is fully backward compatible with all existing standard printf strings. So if you've got printf strings that you're using throughout your application, they should all just work, unless there's an error in them, in which case you'll know right away. But besides just creating the format string, then it also applies that and the arguments to the function that you're trying to call. Another thing it has is this format traits, which gives you the ability to do things like what I mentioned with string view. So the forward args is, so let's just take this standard string example up here. And so any type that has a C_string function will be supported by this. Notice the use of C++20 concepts. And the forward args is how you get it to print, or how you get it the information that printf needs from that type. And then the spec is just how the format string gets rewritten. And then there's a format traits example here for enumerated types. It just prints those as a numeral, and it casts it to its underlying type. And then, if you want to, you can also specialize this further for individual enum types, and you could return a string or something like that instead, and have it print a string. So there's some limited flexibility there on how each type is handled, and it's customizable. All right, so let's do some comparisons. Here's a compiled result of printf. You can see the example code. You've got a string view in there. You've got a int types macro, and then you have the resulting compiled code. And the alternative is to use rostd printf, and as you can see, that's much simpler and more easily readable, safe. And I'm going to switch back and forth between these two slides and see if you can notice any differences between the resulting compiled code. So the only difference, I mean, even the format string is exactly the same. The format string that ends up in the binary itself is exactly the same. The only difference is the symbol name, which is irrelevant because that doesn't get linked into the final binary. It's only for debugging or whatever. So you get exactly the same code, but it's completely type safe. All right, so what's the performance like? Well, first of all, let's say we're talking about compile time performance, not runtime performance. Obviously, if it's exactly the same code, it's going to run in exactly the same amount of time. But we're doing a lot of work at compile time, right? So what does that look like? Well, it's exponential to the number of parameters. This is not actually as bad as it looks, but let me explain. So the yellow line at the bottom is the baseline. So that's just if you're calling printf with that number of parameters. And then the other 3 lines, the orange one is using rostd printf, so the type-safe version with doubles, and the blue one is with integers. And then the gray one is string view. So for each string view, you're actually putting 2 arguments on the printf stack. So the chart goes from 0 to 64, but in the case of string view, for each of those, it's putting two elements on the stack. So that's 128. That's a lot. Most printf statements, you only have a handful of parameters, so it's basically a wash. We do have some code in Roku, some logging code, where there are 50 or 60 parameters to a log. But we tried it. It does take a little bit longer to compile those files, but it's important that the safety is there, and it didn't crater build times. So I was happy with that. And actually, these times are from GCC 10.3. I'm happy to report that we've recently upgraded to GCC 12, and it's about 30% faster. So I assume that compilers will get better at this stuff over time. And I've identified the cause of the problem, and that is it's our use of tuple and tuple cat. But until we can return multiple values from a function without having to put it in something like a tuple, then we have to use that. And it's fine. And okay, so what about format string attacks? Well, it's not really a problem anymore. The format string must be a compile time literal, and it must be because it's a template parameter. And then error checking is inherent in the feature. You can't dislodge it. You can't turn it off. I mean, you can still do stuff like reinterpret cast your parameters and fake it out, but yeah, don't do that. Yeah, and so the result is it's just a single header, 350 non-comment lines of code, and you can download it at that link there. One of my inspirations for doing this was the CTRE library. It's a compile time regular expression. Your phone's ringing, Brian. It's a compile time regular expressions library, and it's a fantastic library. I hated regular expressions before I used this. No matter what you think of regular expressions, maybe you still hate them, but it generates very concise code that just does exactly what you need it to do and nothing more. It's very nice. And I think that's the last slide. But yeah, I would like to point out sort of the gravity of what's going on here. I mean, my example is a pretty simple one, but what you have now is a few powerful language features that allows you to sort of augment the compiler's abilities. So you could even do things like, if you like Rust, for instance, well, you put your Rust code into a template parameter, and then you write code to interpret Rust. And then what you get, if you're any good, the result is not a Rust emulator, it's the actual code as if you had written it in C++ that's generated by the compiler. And that's sort of what CTRE does as well. It doesn't generate a regex interpreter or a state machine or anything like that. It just dumps the code in as if you had written it by hand yourself, the parser. It's really nice. And I think there's a lot more that we can do with these features, and I'm excited to see what those might be, but you have to do them. All right, that's it for me.
We do have time for questions as well, and we have this smart little box that will record you on the internet. So please speak into the black part of it.
Have there been any places in your code where you couldn't rewrite it to use this PrintX?
No. Like what's an example of something you might think of that would cause?
I don't know. It's just
Okay.
my first question when I start to use
Yes.
the libraries. Are there any shortcomings that you have experienced?
Yeah, I mean, the biggest shortcoming is that you have to move the format string into the template parameter. So I've created a very small utility that does that pretty well for most code, but sometimes it slips up. But when it does slip up, it's a compile time error. But like I said previously, it does support all standard printf format strings. It's backward compatible. It sees the length modifiers and it just ignores them and writes the ones that are appropriate for the types that are given. But in our code, we haven't used any non-standard format strings that I can remember, even though I think GCC allows you to use a few extras. I know Windows does as well, but no, I haven't had that problem.
Any other question?
Well, just an example where it would fail or wouldn't be usable if you examine the value of your variable first and adjust your precision. So you runtime create your formatting string. That wouldn't work here.
Yes. So yeah, there are cases where we have runtime generated format strings for better or for worse. Yeah, and we really should address those. Maybe they're appropriate, maybe they're not. But yeah, really what it boils down to is, is it a security risk or not? So yeah, that's definitely one case.
Thank you.
So that almost sounds as if you don't support the width specifier or the precision specifiers. You just discard those as well?
No, those are transferred over byte for byte in the format string. It recognizes those and places them in the correct place in your format string.
Okay, so the example here with dynamically figuring out what the precision should be beforehand, that would actually be doable? No, it would still not, right?
Yeah, I mean, so when you're doing string views, for instance, if you're printing a string view, then it does the percent dot star s, right? So it is using one of those fields, and if you try to use that, I think it's the precision modifier with a string view, it will actually error and say, I can't do that. We need to hijack this part of the format string, and but yeah, everything else it just copies it directly to the so even with the question mark format specifier, if you give it %10.3 or whatever, it will use those as appropriate.
Oh, that's a challenge.
Come on, you can do it.
I don't want to hurt anyone.
Hello. Could you add on to this library so that instead of having these angled brackets, could you, and to make it perfectly interoperable with printf statements, normal printf statements, could you format the string in such a way that it only takes the curly, not curly, but like the normal?
So you're asking if why does it need to be a template parameter?
Yeah, and could you just format the input to match what printf normally looks like?
Yeah, I mean, if what you're asking is, can we just have a change printf so that it reformats this string without having to change it to
Exactly. Yeah.
Yeah. So I'm not a language lawyer, so I don't know the reasons why that can't be done. But I've tried it lots of different ways, and it seems like all the ingredients are there. You can know the length of the string, you can know the contents of it without making it a template parameter, but you can't put those together to create a type which contains the length of the format string that you need to generate in order to fill that buffer with the correct What I would suggest is that you download my code and try it and see if you can get it to work.
And just so that it's to be clear, I think you said row standard printf, but is that exactly the same as PrintX?
So the PrintX is, yeah, that's kind of a, that's an internal name we used at Roku, sort of as the prototype of it. And rostd is our extensions, sort of extensions to the standard library. Every company has, every large tech company has their own. And this happens to be one of the first things that's gone into it. And as it did, we just changed it to be rostd printf. But the utilities themselves, like the format literal definition, are inside of a PrintX namespace inside of that. And that's where the name still remains. But yeah, really what this is it's just an overload to printf. It could go alongside the standard library, right alongside printf, and fully backward compatible. But yeah, like I said, you should download the code and see if you can get that to work. Yeah, and if you do, I'll buy you a beer.
All right, we've run out of questions. Cool. Well, thank you very much, Aaron.
Yeah, thanks for having me.
Well, good to see you.